Good morning, everyone. Today we are going to continue our talk about polymer structures, and we have spent one session on the first part of polymer structures. And today we'll continue our talk. First, I want to refresh your memory about molecular weight calculation. So this is the example I gave you last time. So here, for example, average mass of a class. So this student, this is student index, and so this is their corresponding weight, the mass in pounds. What is average weight of the students in this class? First, based on the number fraction of students in each mass range, and second one is based upon the weight fraction of students in each mass range. This weight fraction and number fraction. I wanted to use this example to illustrate on how we calculate the weight for the molecule. For this is a solution. The first step is to sort the students into weight ranges and using a 40 pounds range, giving the following the table. So this is a weight range, mass. So this is a mass range, the number of students, and that 4 into this is the mass range, weight range. And so this is the mean weight for each of these weight range. You can see some weight ranges do not have any mean weight because no students fall into this is 3 the weight ranges. So calculate the number and weight fraction of students in each weight range as follows using this equation. This xi, this is the number fraction, wi is the weight fraction. Weight range, I'm sorry. So for example, for the 81 to 120 pound range, and we use this one, this is a subscript, and 81 to 120, and 2 over 12, right? We have 2 students fall into this range, and then total number of students equals 10, then so this fraction equals 0.2. And similarly for weight range, W18 to 120, weighting to 120, we just calculate two students that have this kind of range, and then divide by total mass. So this is total students, and this is the total the weight of these students. And so this equals 0.11117. Then we use this equation to calculate, and all this is the number fractions for these different weight ranges, and we get a number fraction and a weight fraction Wi. And then we can calculate this is the number weight, and also this the molecular weight based on the weight based on number fraction, the weight based on the weight fraction. So we can get these two values. So 188 pounds, and so this is 218 pounds. So we can have two different values, and these will have two different values. And then we talk about the degree of polymerization, dP. And the degree of polymerization, as the name suggests, it is and shows how many pairs we have combined them together. So this is average number of repeat units per chain. So this one, average number of repeat units per chain. Polymerization, as I told you, polar means multiple, mer means the repeat units. And so here for this one, so dP equals 6, and we have 6 for this chain. And degree of polymerization equals 6. So dP equals, how can we calculate the dP mathematically? We use this Mn. So this is the number of weight. So this is the molecular weight based on number fraction, and divided by M bar. M bar is average molecule weight of the repeat unit. If we have this one of a total of chain, and so this one is average molecule weight of repeated unit for copolars, that is calculated as follows. So this m bar equals chain fraction, right? This is a chain fraction. So m is a molecular weight of the repeat unit. So if we use this equation, we can get this m bar, and then we use this equation and to get this dp. Any questions regarding this slide? No question. We talk about molecular structures for polymers. We have four different molecular structures for polymers. For first one, we have linear. The chains are linear, and the interchain force is secondary, which is usually very, very weak. Second one is a branched. You can see this is a chain, the bone. This is a bone chain, and on each of these bone chain we have some branches. So this is called a branched structure. The third one is a cross-linked. And cross-linked, we have the backbone chains here, and we also have several molecular these branches. So these branches, some branches, and they connect some of these the chains here. The difference between this one is that for this category, the chains and they are not connected, even though each of them they might have branches. But for here, they are branched. The fourth structure is network. So you can this network. So all these chains, they are networked together. Polymer molecular shape. So molecular shape or conformation, molecular shape or conformation, okay, conformation, and chain bending and twisting are possible by rotation of carbon atoms around their chain bond. So this is the called molecular shape or called conformation, and you should know this if in our following quiz or exam, if I talk about this conformation, you should know what I'm talking about. Look at here. So this is the chain, back chain here. You can see for each of these carbon atoms, they have multiple possibilities, right? For example, for this carbon atom, so this can be here or can be other places on this circle. The same thing for this one. Can also on any point of this is a circle. So this is called molecular shape or conformation. So this is a chain end-to-end distance and chain end-to-end. So here is the chain, right? This is a chain, and they might be tangling and on some portions, but so this is end, this is end. So this R is a straight distance between these two ends, which is called end-to-end distance. Molecular configuration for polymers, configuration confrontation, and configuration to change must break bonds, and to change you must break the bonds. So first one we talk about stereoisomerism or stereoisomerism. Okay, stereo. So this one CCHHHR. So this is radical. This is radical. R is a radical here, and go here. And we have HH. So this is you can see. Okay, this is a double bond, and or this is it goes this way. So you can see these are the difference between this structure and this structure is that is the position of R. So this R is below the chain backbone chain. So this R is above the backbone chain. So this means that this double bond is possible to be this one or this one. And then we talk about tacticity. Tacticity is called stereo regularity or spatial arrangement of this radical using unit along these chains. And so isotactic, so this is tacticity, okay, so this is very, very special term and you need to know after we finish today's class. Isotactic, all R groups on same side of chain. So this either. Either in English language, either means that something is the same, or something has the same form, or something the same position, or this either. Here in this context, either means all R groups on the same side of the chain. You can see here, R they are on the same chain. Okay, here, so this one is more intuitive. We can see R here. They are on the one side of the backbone chain. This is called isotactic. Another one is a syndiotic, and R groups alternate sides. And if we use this one, this is a schematic representation of this backbone chain here. You can see R, this alternating on top side or below side, top, bottom. And if we use this one, you can see R is here. So this is R. Okay? So this is R. And so this is R. And so this is R. And so this is R. So this is called syndiotic. And syndiotic means this R and H. You can see here, this guy, R and H, HR, RH, HR, RH. And tactic, a tactic, and we can know that if we put something, put in front of something, and we usually this means this none is not tactic. So here means that R groups randomly positioned. And for example, using this one, this R is here, this R is here, and then this R is here, and this R here. That means we cannot find any the rules that and we can predict the position of this R along this backbone chain. So in this context, we call a tactic. And we can see here, R is here, R is here, R here, R, and R. This is a tacticity. And also, this is a since and trans isomerism. And since and trans isomerism. So here is a double bond here. So this is the CH2, CH3, H, CH2. So this is double bond here. So this is cis isoprene. So this is cis isoprene here. Here, this one is the trans CH3, CH2, CC, H, and CH2. And what is the difference between these two? And the difference is that here H atoms and the CH3 groups on the same side of the chain. This guy and this guy, they are on the same side of the backbone chain. The backbone chain we see as horizontally. It's horizontal backbone chain here. So this trans isoprene, the got a picture. H atoms and this CH3 group, they are all of this side of the chain. So this is how they are different. And since trans isomerism. And then we talk about this is characteristics of polymer molecules here. And we know, okay, so you can see molecular characteristics, chemistry, repeat unit, size, molecular weight, shape, chain twisting, entanglement, etc. Structure. We talk about linear, branched, cross-linked network. And then based on this one, we have isomeric states, and we have stereo isomers, or these are geometrical isomers, and the stereo isomers, and we have isotactic, syndiotic, along with atactic. For the geometric isomers, we have since and trans. And now we have talked about several important concepts in this lecture. So I want you guys to know what these concepts are and how they are different from one another structurally. Okay, so supposedly you should be able to tell me what this structure is if I give you the structure visually, and then you just tell me what the structure is, this one is. Do you understand? Okay, don't want you guys just to listen to what I'm talking about. I want you to understand. As I said, if I give you a structure or structures, and if I ask you, tell me what's the structure this polymer has, and you should be able to use your own language, tell me what structure it is and why. This is very, very important. And this is VMSE is our old friend. And as I said, if you have bought your textbook, and you should have this resource that accompanied with this your textbook. And also here, you can see stereo and geometric isomers. So this is very, very beautiful, intuitively, and give you a better idea what these isomers are and how they are different structurally, and you will like this one very, very much. And then we talk about copolymers. And copolymers are two or more monomers polymerized together. Right? So, and previously we talk about the polymer, and polymer means that we only have one single repeat unit. But here we have two or more monomer single repeat unit. And so we can see here random. This is a mer A, mer B. Okay, A and B randomly positioned along chain. So you can see here, you can see this one red, this one mer, and this is the dark is another mer, alternating, 1A, 1B, 1A, 1B, 1A, 1B, alternating. A and B alternate in a polymer chain block. Block means large blocks of A unit alternate with large blocks of B units. So this is a block graphed, and chains of B units grafted onto A backbone. So this is called graft, and this is called graft. Any questions regarding this slide? Because it's called copolymer. As I said, and this one is different from the polymer we introduced before. I also told you guys how the polymer is different from copolymer. Okay, the difference is for polymer we only have one single the same repeat unit. For copolymer we might have two, mer A and mer B, and they can be arranged randomly, alternatingly, blockly, or graphically. Any questions so far? No question? And then we talk about crystallinity in polymers. Crystallinity, this kind of strange to some if we have not heard this one in polymer, and this concept here might be strange to some students. When I was a student, when my professor talked about this one, I also kind of shocked. But now I know, I understand. Okay, so crystallinity in polymer. Crystallinity usually happens in the metals or metal alloys. But in polymer, because it is very, very difficult to arrange these items to the chains periodically, and sometimes most of the time we do not have crystallinity. And however, if based on some the techniques processes, we might have crystallinity in polymer. So here, crystallinity, as the name suggests, it means ordered atomic arrangements involving molecular chains, ordered, repeated, periodical, and crystal structure in terms of unit cells. Crystal structure in terms of unit cells, unit cell, right? When we talk about crystal structures for metals and metal alloys, we talk about the four commonly seen crystal structures: IC, simple crystal structure, BCC, body-centered crystal structure, FCC, face-centered crystal structure, and HCP. And we talk these are four commonly used crystal structures for metals and metal alloys. And here also we have crystal structures in terms of unit cells. So example shown here on polyethylene unit cell. This is polyethylene, okay? So you can see, and we can see clearly, and so they are ordered, and this is repeated pattern for the arrangements of these atoms. And we can see this is called unit cell. And this unit cell, and this is a 3D unit cell. We have three lengths, the width, along with the height of this unit cell. So this slide shows the crystallinity in polymers. Any questions regarding this slide? Then we talk about polymer crystallinity. Crystallinity regions are thin platelets with the chain folds at the faces. So thin platelets, lead droplet, this is a small drop. Platelet means the small plate, and you should know that. Okay, this is very, very interesting, and is a very, very good way for us to understand this word if we first see this word. Plate means a plate, right? Plate. Lead means a small plate with chain folds at the faces. The chain folds, this small plate. The chain folded structure, the chain, you can see the chain goes this way, folded periodically. So the thickness is 10 nanometer. On polymer crystallinity continued. On polymer rarely 100% crystalline, and as I told you guys, right, it's a polymer is different from metals and metal alloys. Difficult for all regions of all chains to become aligned. Aligned here means arrange them periodically or based on some predictable patterns. So here you can see here this one is chain crystalline region because we can see and the predictable pattern. This region also a region of high crystallinity, and here is amorphous region. Amorphous is non-crystalline. So this is crystalline, and all other areas they are amorphous region. And then if this is a total region or domain, we have both crystallinity and also amorphous region. And there is another concept that comes up, and degree of crystallinity. So this is expressed as the percentage of the crystallinity. So some physical properties depend on percentage of crystallinity. So this is understandable because we know that even for the same material, if this guy is in the form of crystallinity, and this guy will have this set of mechanical properties. And however, even for the same material, if this material is in the state of amorphous material, so this guy will have another, might be distinctly different set of mechanical properties, right? So some physical properties depend on percentage of crystallinity. This is understandable. And heat treating causes crystalline regions to grow and percent of crystallinity to increase. So it means that if we heat this material, more and more regions will become crystalline regions from amorphous region. And you should know that this increase, okay, is if we heat treat this material, the crystallinity region will be growing. So in one direction, growing, not decreasing. Be very, very careful about this statement. And then we talk about the polymer, the single crystal. A single crystal, that's awesome. That means for all these polymer, we only have one pattern. So this is very, very awesome one, right? When we talk about single crystals in metals and also metal alloys, and we know how this single crystal affect so the mechanical properties. So here is electron micrograph. This is electron micrograph. Multi-layered single crystals, chain-folded layers of polyethylene, chain-folded. And single crystals only for slow and carefully controlled and growth rates, and single crystals only for slow and carefully controlled growth rates, because a single crystal means that within this region, you only have one single pattern of arrangement of these chains. That means when we compare this one in this single crystals for metals and metal alloys, we know that so this one single crystal is much more difficult to be achieved. And then we talk about semi-crystalline polymer. What is a semi-crystalline polymer? Some semi-crystalline polymer from spherulite, the structure. And spherulite, right? What is a spherulite? If I don't tell you anything about spherulite, and based on your English language learning experience and what concept appears in your mind, spherulite, and this is sphere. And sphere, in my word, in my knowledge, sphere means a circle, right? It is a circle. You can see spherulite structure. Martensite, this is another spherulite. You can see the alternating chain folded crystallines and amorphous region. This crystalline, amorphous, crystalline, amorphous, crystalline, amorphous. So all these guys, they are forming a sphere. That's called a spherulite. And spherulite structures for relatively rapid growth rates. So here is a nucleation site in the center. Nucleation site. So this is inter-spherulitic boundary. So here, inter-spherulitic boundary. Okay, spherulitic boundary. So this is just like the boundary, the green boundaries we have seen in the metals and metal alloys. So this is a new word, spherulitic, and direction of spherulitic growth. Okay, spherulitic growth is normal and to the sphere, the surface of the sphere. This is the direction of the spherulite growth, alternating of crystalline region, and this is the amorphous region. So this picture shows the spherulites in the polyethylene. So this is a micrograph. You can see here. So this is the cross-polarized light used. We use this one. So here you can see this is the mantis cross appears in each spherulite. Right? For each this is spherulite. Any questions so far? If no question, and I'm going to see you this Friday. And keep in mind, so this lecture is very, very important. We have learned several new concepts, and you should know these concepts and know how they are different and what they are referring to. Thank you very much, and I appreciate your attention and time, and I will see you this Friday. Bye.